Hey there, Jim Caffey here with Chapter 8 in the Essential Cosmic Perspective. This is on the Jovian Planet systems, Jupiter and Saturn, Uranus and Neptune. So our goals for learning for this chapter are, what are the Jovian planets made up of? And what is the weather like on these Jovian planets? So we have Jupiter and Saturn, the gas giants, made up of mostly hydrogen and helium. And then we have the ice giants, Uranus and Neptune. Notice how I pronounce Uranus, not Uranus. That's how we pronounce it. You can imagine why. So Jupiter and Saturn mostly made up of hydrogen, helium, like I said, and the Uranus and Neptune made up of mostly hydrogen compounds, water, methane, and ammonia, and some ice, helium, and rock. So beyond the frost line, the planetesimals could accumulate ice, like Uranus and Neptune, and the hydrogen compounds are more abundant than the rock and the metals, so Jovian planets got bigger and acquired the hydrogen and helium atmospheres, since the universe is made up mostly of hydrogen and helium. Now the Jovian planet cores are very similar. They are the mass of about 10 Earths, but the Jovian planets differ in the amount of hydrogen and helium gas accumulated. So the question is, why did that amount differ? Well, it has to do with the timing effect. The planet that forms earliest captures the most hydrogen and helium gas. The capture ceases after the first solar wind blows the leftover gas away, and that was the case for Jupiter. The planet that forms in a denser part of the nebula forms its core first, and again that was Jupiter. So inside Jupiter we have a high pressure inside of Jupiter, causing the phase of hydrogen to change within the depth. So on the outside we have the cloud tops, of course, and then we have the gaseous hydrogen right beneath that, and then it goes to a colder liquid hydrogen, much like was used to launch the space shuttle. And then inside the core it's so dense it's called metallic hydrogen. And this metallic hydrogen generates the magnetic field around Jupiter. So hydrogen acts like a metal at great depths because of these electrons move freely. The core is thought to be made up of rock, metals, and hydrogen compounds. And the core is about the same size as Earth, right down here, but 10 times as massive. So comparing the Jovian interiors, the model suggests that cores of Jovian planets have similar compositions, but the lower pressures inside Uranus and Neptune mean no metallic hydrogen for them. They instead have an icy core. Now Jupiter does have a very massive magnetic field called the Magnetosphere. And so Jupiter's strong magnetic field gives us an enormous magnetic field. And the gases escaping Io, one of its main moons, feed the donut-shaped Io torus. And what this means is that Io generates a donut-shaped size magnetic field that interacts with Jupiter's and creates some dynamic effects. Well, what is the weather like on these Jovian planets? Of course, we have the Great Red Spot on Jupiter, and we'll talk about that in just a minute. So Jupiter's atmosphere, we know this because we've actually sent a probe to Jupiter's atmosphere. The spacecraft called Galileo was launched in the 90s and reached Jupiter, and one of the things it did was send a probe through the atmosphere. So we know that the hydrogen compounds in Jupiter form clouds. We know that different cloud layers correspond to freezing points of different hydrogen compounds, and we also know that other Jovian planets have similar cloud layers. So Jupiter in its colors, we have ammonium sulfide clouds. They reflect a red and a brown, and ammonia, the highest, coldest layer, reflects white. For Saturn, Saturn's layers are similar but are deeper and in fact farther from the Sun, so they are more subdued, not as many layers. Now on Uranus and Neptune, the methane that forms absorbs red light but transmits blue light. So we see these planets as blue. The blue light reflects off methane clouds, making those planets look blue. So here is Jupiter's Great Red Spot. It is a storm twice or even 3 times as wide as the Earth is in whole, a massive hurricane. And it has existed for at least 3 centuries, back to the time of Galileo and probably before him too. The weather on the Jovian planets have strong winds and storms. All of them do. So what did we learn in this section? We learned that Jupiter and Saturn are mostly made up of hydrogen and helium gas. Uranus and Neptune are mostly made up of hydrogen compounds in the form of ice. They have layered interiors with very high pressure and cores made of rock, metals, and hydrogen compounds, and the very high pressure in Jupiter and Saturn can produce metallic hydrogen, which reinstates the fact that they have a magnetic field. Multiple cloud layers determine the colors of these Jovian planets, and they all have storm and winds. Now for the satellites, the moons of the ice and the rock planets. What kinds of moons orbit the Jovian planets? What are the Jovian Galilean moons geologically active? What geological activity do we see on Titan around Saturn and other moons? And why are Jovian planet moons more geologically active than the small rocky planets like our own moon? So we here have the 4 Galilean moons of Jupiter. We have Io and Europa, an ice moon, Ganymede, and Callisto with lots of craters. Now these small moons have no geological activity. The medium-sized moons have geological activity in the past, and the large moons have ongoing geological activity. So are these medium and large moons enough self-gravity to be spherical? They have abundant amounts of ice. They formed in orbit around the Jovian planets, Jupiter and Saturn, and the circular orbits in the same direction as the planet rotation. Makes sense? These smaller moons are far more numerous than the medium and large moons and are not enough gravity to be spherical. They are in fact potato-shaped. So why are the Jupiter's Galilean moons so geologically active, these 4 big moons? Let's look at Io. Io is the most volcanically active body in the solar system. But why? This moon around Jupiter has many active sulfuric acid volcanoes, and we want to know why. These sulfuric eruptions continue to change Io's surface. Io is so close to Jupiter that it is squished and stretched as it orbits Jupiter. And so the interior of Io is continually being disrupted and gravitationally pulled and pushed together to form new eruptions. But why is the orbit so elliptical? Well, we know Europa's ocean is a water world. This is a moon with an ice-covered layer about 10 times as thick as the Antarctic. So it's about 60 miles thick of ice, and below that we believe it has a saltwater ocean. So the surface is constantly being recovered by water ice. These tidal stresses crack Europa's surface ice, allowing the water from below to come up to the surface and recover it and refreeze. Europa's interior was also warmed by tidal heating by the planet Jupiter. Ganymede is the largest moon in the solar system. Clear evidence of geological activity and maybe tidal heating plus heat from a radioactive decay possible in the interior of Ganymede. And now Callisto is a classic cratered ice ball, an icy surface with craters on it. It's far enough away that there is no tidal heating, no orbital resonances, but it does have its own magnetic field. Well, what does that mean? Well, what other geological activity do we see on Titan, around Saturn, and other moons? As you see, as we go along these PowerPoints, you're going to be asking yourself many questions. And so the questions are, why are these things happening? Well, you're going to have to read about these in the book. And you're going to have to watch the lecture videos that I produce to see why these are happening. So Titan, this is Saturn's biggest moon, and we have actually sent a probe to Titan. The planetary probe called Cassini, launched from a Titan rocket from Cape Canaveral in Florida, put off a probe that landed on an icy beach of Titan. Titan is the only moon in the solar system that has a thick atmosphere. Let me rephrase that. Titan is the only moon in the solar system with a thick atmosphere. Why does it have this thick atmosphere? It consists mostly of nitrogen, with some argon, methane, and ethane. And the beach this probe left on was a ethane and methane beach. So on the surface, these are real pictures from that probe. The Huygens probe provided a first look at Titan's surface in the early year of 2005. And it has liquid methane and rocks made up of methane ice. Titan also has methane lakes, and radar imaging of Titan's surface has revealed dark, smooth regions that may be lakes of liquid methane. I can tell you now, that's exactly what it is, liquid methane. The medium-sized moons of Saturn almost all show evidence of a past volcanism and or plate tectonics. This includes Mimas, which looks like the Death Star of the Star Wars, Enceladus, a very active icy moon, Tethys, Dione, Rhea, and Iapetus. Fountains of ice particles and water vapor from the surface of Enceladus indicate that geological activity is ongoing, and it surely is. We see this all the time from the Cassini spacecraft, which is ongoing around Saturn. There are varying amounts of geological activity occurring on these medium moons. The moon Miranda has large tectonic features and few craters. Now, what has happened on Miranda? Here we have a moon that has been impacted by something in the past. It has completely fallen apart and recollected itself from the interior within to the outside. So these parts here, the northern hemisphere, this part down here in the south, this is from the interior of the moon. And so this is indicative of tidal heating in the past. And now we look at the furthest planet from the Sun as of this recording in June 2015. And of course, I say that because of Pluto's incoming encounter with this spacecraft. Neptune's moon Triton. Now, don't get confused between Titan on Saturn and Triton on Neptune. So, Neptune's moon Triton is similar to Pluto but larger, and it has evidence of past geological activity. And in fact, on Neptune's moon Triton, we find volcanic craters exhibiting nitrogen gas coming out from them. And we see these nitrogen gas streaks coming out of these craters on Neptune's moon Triton. So why are the Jovian planet moons more geologically active than the small rocky planets like our own moon? Well, the rock melts at higher temperatures, and only large rocky planets have high enough heat for this activity. The ice melts at lower temperatures, it's far enough away from the sun, and the tidal heating can melt internal ice, driving that activity. So in this chapter we have learned that the moons are of many sizes around the Jovian planets, and they have different levels of geological activity depending on size. The tidal heating of these moons drives activity, leading to Io's volcanoes and the ice geologically of other moons. Titan is the only moon with a thick atmosphere around Saturn, and many other icy moons show signs of geological activity. Why are these Jovian planet moons more geologically active? It's because the ice melts and deforms at lower temperatures, enabling the tidal heating to drive activity, being so close to these big gas giants. Now let's take a look at the Jovian planet ring systems. What are Saturn's rings like, and why do all the Jovian planets have rings? We know these rings around Saturn are made up of numerous tiny individual particles. They orbit over Saturn's equator, and they are very, very thin. An Earth-based view of Saturn shows that this looks like a large concentric rings, but in fact, these are very individual particles orbiting Saturn, and this gap in the middle here is called Cassini's division. A spacecraft view of the ring gaps shows many individual rings separated by very narrow gaps. An artist's conception of the close-up shows these particles clumping together because of gravity, but small random velocities cause the collisions to break them up. And then we have the gap moons. Some small moons create gaps within the rings and generate their own gravitational force. So why do the Jovian planets even have rings to begin with? They all do. All 4 Jovian planets have ring systems: Jupiter, Saturn, Uranus, and Neptune. Others have ring particles that are smaller and darker than Saturn, such as Neptune's. They form from dust created in impacts on the moons orbiting these planets. But how do we know this? We know that the rings are not left over from the planet formation because the particles are too small to have survived this long. There must be a continuous replacement of tiny particles from these moons, and the most likely source is impacts within the Jovian moons. So the Jovian planets all have rings because they possess many small moons close in. The impacts on these moons are random, and Saturn's incredible rings may be of an accident of sorts of our time. So we learned that Saturn's rings are made up of countless individual ice particles, and they are extremely thin with many gaps. The Jovian planets have rings because these ring systems are much fainter, with smaller, darker, and less numerous particles, and the ring particles are probably debris from other moons. That's it for Chapter 8.